But before that, let's take a quick little water break, see how we're doing. Okay. All right, we're doing good. Okay. So let's switch back over. And let's see now. We have, what are the Lewis structures for the following compounds: NO2 plus and NO2F. Okay. So first, let's just tackle the NO2 plus. All right. So nitrogen has 5 electrons because it's on the 15th column. Oxygen has 6 electrons because it's on the 16th column. So each one, this one will be donating 5 electrons in the valence. Oxygen is 6 times 2, that's 12. But this plus right here means that we're actually going to have 1 less electron to work with. So rather than just being 17, we're actually going to work with 16 electrons. Okay, that right there is important because that actually tells us whether we're approaching this correct or not. So that being said, let's just go straight to the Lewis structure. We're now going to have N in the middle, all right, and then the 2 oxygens on each side, and we're now going to add the bond there. Okay, so now the oxygen is sharing 1 of its 6, so 2, 3, 4, 5, 6. Same thing here, 2, 3, 4, 5, 6. Okay. Nitrogen, on the other hand, is sharing 2 of its 5, so 3, 4, 5. But as we said, there's 1 electron less. I'm just going to take off this one here. What this allows me to do is see this and see there's 4 unpaired electrons right now. So I can actually use these to form a double bond between each oxygen and nitrogen. So if I redrew this, it would actually look like this. Okay, just redo that. Okay, we have the oxygen, we have the other oxygen, and there's nothing on the nitrogen anymore, and we have now a complete oxygen on each side. Okay, and if we went ahead to do the formal charges, the oxygen would be 6 valence electrons minus. It has 4 to itself, 4 electrons, and it's sharing 4 for each oxygen, so that is coincidentally the 0. Perfect. The nitrogen, on the other hand, 5 valence electrons. It has 0 to itself, and it's sharing 8. So that is indeed +1, which is how NO2 is a +1. It's actually on the nitrogen. So this is indeed the Lewis structure for NO2+. Now, they do ask us to include all the important resonance forms. So, in order for this, there are possible forms, but if I drew that resonance, it would no longer be following the octet rule. For example, if I moved, okay, yes, if I moved one of the double bonds, okay, to made into a single bond, and the oxygen was like this, where it was just 1 bond between them, and now nitrogen had that. Although this could be a resonance form, this doesn't really work because this oxygen here is no longer following the octet rule. So this couldn't really work. And even the nitrogen wouldn't be either, because now it has 10 electrons instead of 8. So that wouldn't be it. So looking at this, this is the most stable and frankly probably the only resonance structure it can form, because any other thing would break the octet rule. But let's look at NO2F now, okay? We were given a lot of hints based on just the NO2, but to see what NO2F is, Let's find out. So that one would be, as you see here, we have to first count the electrons. It's going to be 5, 12, and fluorine's on the 17th column, so that's 7 electrons. So actually now we have 17 plus 7, that would be 24 electrons total. Okay? So now with that being said, we're going to put the nitrogen in the middle again, because it has the most unpaired electrons. And we're now going to surround it with the 3 things. So we have O, O, and F. Okay? So now oxygen is going to be, well, it's going to have two. Sorry, I'm blanking out. Oxygen now have sharing one of its 6, so that's going to be 2, 3, 4, 5, 6. Same thing here, 2, 3, 4, 5, 6. And now the fluorine is going to be 2, 3, 4, 5, 6. Oops, too close. 6, 7. And nitrogen is right now sharing 3 of its 5, so 4, 5. So the only lone pairs here are these 2. Oops, yep, this one here and that one there. So we have to figure out a way to take care of this. Nitrogen is already full, so that one wouldn't work. But what we could do actually is that if we kind of split this and just gave an electron to the oxygen, well actually if we made this one into a bond here, so these ones bonded together, and we just gave this electron to this oxygen, we could fit our octet rule for everything here. So what we would have now for our picture, and just to make sure I'm doing things right, I'm actually going to go ahead and count the electrons for the previous question, because we do have 4, 8, 12, 16. Perfect. Okay. So now we have the nitrogen here. Okay. We have this bond still, this oxygen above, comfortable now with its octet rule because it just took that one electron, and this oxygen here comfortable as well with the octet rule because this has a bond, and the fluorine just staying as a fluorine. Now with that being said, this one now can have possible resonance structures. As soon as I just move this out the way, this work out the way, put this under here. So what do I mean by resonance structures? Let's find the formal charges of each. So first thing, the oxygen to the left, that one's going to be, as we did, 6, okay, minus, has 4 to itself, plus 4 over 2, so that is 0 still, perfect. The oxygen above, it's still 6 valence electrons, but now it has 6 to itself, and it's sharing 2, okay? So that one would be, not 0, sorry, it'd be minus 1. So that oxygen above has a negative 1 charge. But that means something here has to have a positive charge. Let's check the fluorine. So the fluorine is going to be 7 minus, it has 6 to itself, 2 over 2, that's going to be 0 as well. And now the nitrogen has, it's going to have, sorry, I'm blanking out, 5, and it actually has 0 to itself, and it's sharing 8. So that's going to be 4, so that's going to be plus 1. And that's where our positive charge is to cancel it out. So we have a minus 1 and a plus 1. So now similar to the other question to how we could not make it in a way to where the nitrogen would be able to fill its octet rule, that one is not going to be bothered with the formal charge differences. We're going to just start rearranging everything in terms of the resonance structure. So this is one resonance structure. Another one would just be to make negative on the other oxygen, okay? So that would be, we switch these around, we have now the oxygen single bonded here at the end on the left with the nitrogen, okay? And then this one's the one that has a double bond. That is another possible resonance structure because now The negative is going to be here. The positive is still on the nitrogen. Now there is another resin structure we can do as well. That's a little bit wonkier, okay? Is if we made it so that both oxygens actually had a single bond and there was a double bond with the fluorine, okay? And you notice that at the end of the day, everything should still add up to 0 for the formal charge. So as you can see, pretty much all I've been doing is moving a double bond to, like, as in making it take the whole double bond, and then also making something else give up its lone pair to form a double bond. That's how I move it around. But fluorine now, because that happens, you would actually calculate its formal charge. You would see that this now is going to be 7 minus, okay, it has 4 to itself, and it's sharing 4. So it's actually going to be a plus 1. And so you'll see here that just as how we have now 2 minus 1s for the oxygens, nitrogen still stays plus 1, but so is the fluorine now. We have 2 minus 1s and 2 plus 1s. These are, at least from what I can see, all the possible variants of the formal charges you can have that still follow the octet rule for NO2F. So let's now check and see how we did. Okay, we have, let's see here. Ah, okay, I see what they did now in terms of this. The way they did that is that they moved it to form a triple bond. Ah, so they put the bond in there, so it still follows the octet rule, and they kick the bond out. That makes sense. So just as how we did here, there are actual little structures we can do, just as what they did there. So it's important that, just as how I was struggling earlier, you want to make sure that when you do move a double bond into the, I guess, the outer part, I mean, when you move a pair out, you have to push a pair in. So one of them, as they showed there, will be oxygen, now with a single bond between the nitrogen, but that means this one has to be a triple bond, because this oxygen is going to be the negative, and this oxygen is going to be a positive. And you'll see that in total, we have positive here, negative here, and that's going to be a plus 1 total. And if you inversed it, it still counts as a different resonance structure, because now it's going to be oxygen on the right that has the single bond. So we have now positive here, and a negative there. So we have 3 resonance structures here. And then for this one, exactly, we do have the 2 resonance structures as they mentioned, where it just keeps switching. But exactly, this will be the 3rd proposed resonance structure, to where the fluorine is the one that has double bond, because it still follows the octet rule. This is just the one that's the least favored, so this one will be the least favored because of the fact that now fluorine, which generally just prefers to have, you know, a charge of like 0, as you can see, this form here has the most, I guess, different formal charges, to where there's like, you want the formal charge to be as close to 0 as possible, as you want as many zeros as possible in your formal charge calculation. And this one's just all over the place, to where it's like plus 1 here, minus 1 there. So that's why this one wouldn't work. Now, in regards to this, as we mentioned, when we kick a double bond out, it has to be replaced somewhere. So these are all the variants of the formal charges here. So this is correct. Although they are missing one form with the fluorine, technically they did show me the other 2 here that I was missing. So just make sure that you account for every possibility, meaning that try your best to see what happens when you move a pair out, as in towards one of the outer atoms, and then move a pair in from just any other of the outer atoms as well. So that's it for number 16. Let's see now what we're doing. We have number 17, which is relatively straightforward. It's asking if I'm going to stop here for today, but just answer number 17. Is there a charge in H2O? So for this one, we can actually approach it in different ways. We can use the oxidation numbers, or we can use its formal charge as well. Because oxidation number is relatively straightforward, we have H2O. Funny enough, there's actually rules for it. So oxygen likes to be -2, except for in hydrogen peroxide, which this is not. So we have a formal charge of -2, -2, and we're assuming here, actually, oxidation would not work because that assumes that we have a net charge of 0. So instead, we're going to use our formal charge. So with that being said, to use formal charge, we need to find its Lewis dot diagram. H2O, H in the first column, so that's 1 electron each, that's 2 electrons. Oxygen, 16th column, 6 electrons, so we have 8 electrons total. Okay, so now we're going to put oxygen in the middle. We're single bond with the hydrogens. So with that being said, the hydrogen is actually now complete because it's sharing one of its 1 electron, so we don't need to add any more. But oxygen is sharing right now 2 of its 6, so 3, 4, 5, 6. Okay, so this right here would actually be the completed version of what a Lewis structure for oxygen would be. There would be no moving around the electrons because of the fact that hydrogen actually doesn't want to take more. I don't think it even can. So with that being said, there's no way to move anything else. Let's calculate on the formal charge. So the way you calculate formal charge is done with this formula: valence electrons minus, okay, and then parentheses, not really lone pairs, but electrons not shared plus electrons shared over 2 though, and that is going to be your formal charge equation, and the goal is to have it equal to 0 hopefully, or else it means it has a charge. So if we do the hydrogen first, we have 1 minus, it has no electrons that it's not sharing, so that's 0, and it's sharing 2 electrons, so 2 over 2, that equals 0. Perfect. And now for the formal charge of oxygen, so this is hydrogen, oxygen is 6 valence electrons, it has 4 by itself, and because they're sharing 2 on each side, that's 4 in total. So that indeed does equal 0 as well. Okay, so because the formal charges for both are 0, this means that H2O, water, has no charge. So the answer is no. Okay, and that is what they got here. They used the oxidation states, but the oxidation states is assuming that we have a net charge of 0. So that one can be good to use, but I would actually go with the formal charges because that at least allows us to use a concrete information that we're given to be able to find that. So with that being said though,